Hello everyone, my name is SHARJEEL Ahmed. I am from Pakistan. Today I will present the topic UV light triggered fluorescence coatings for early detection, corrosion detection in AA202 2024 T3 based on VCO2. So here are the contents of my presentation. First I will discuss the introduction, then research backgrounds, then problems and objectives, and then results and discussion, and finally conclusion. First of all, introduction. So what are fluorescence corrosion detection coatings? These are coatings that can detect the corrosion when put into the UV environment. So these are three types of the coatings. One is pH based, and second is metal ion based, and now the recent is dual responsive. And there are some applications and the mechanism. We will discuss further one by one. So importance of the fluorescence corrosion detection coating. So why do we use the fluorescence coatings? Because it doesn't require any contact with the material during the detection. It is highly sensitive and it only requires simple visualization, because the all previous methods they require too much heavy industry and machines and expensive methods. So this is just a simple visualization. So what happens in this case, when the fluorescence coating put into the UV environment, it shows some bright fluorescence effects by changing the structure from isomerism. Okay, so what are the research problems? The indicators have some prematurely indicators, because there are some indicators that may be some prematurely activate, and their chemical species such as functional groups can react with the components that cause quenching, and slow fluorescence response rate, unclear visibility of the fluorescence, defects in the coatings that such as scratch and bubbles, and sensitive to the environment. So we will solve all these problems, and that are our objectives. So fluorescence agents should be the complex with the metal ions to enhance the fluorescence, and corrosion integrator should not possess any functional group such as phenol group, and all the problems we will solve. So this is the synthesis scheme we have made for this. Like, we have used the vanadium oxide as the precursor and oxalic acid as the reducing agent, and DMF and PG4 we have used as ingredients to prepare these UX quantum dots. And then we have prepared the CO2 and we have used the CO2 nitrate ascorbic acid as the reducing agents, and same DMF and PG3 as the ingredients. So we have prepared CO2 nanospheres. Then we combine all these materials in the vacuum conditions to merge them to functionalize them, and these are the resultants preparation and the fluorescence effect. So here is the SCM mapping that shows that our ingredients has been successfully formed a spherical shape. In this SCM we can see that the VUX nanorods has mounted on the in a spherical circle shape, and CO2 nanospheres are also mounted on this in very beautiful pattern. And the EDS mapping also confirms that it contains vanadium, oxygen and CO2 particles. To confirm this characterization, we have performed the XRD, Raman and XPS spectrum. All these characterization confirm that our prepared metal has all the characteristic peaks, and the survey also can shows all the materials have their own characteristic peaks. And the O1X also spectrum shows that it has dual bonds. In the case of VCO2, V bonded CO2, that one is V bond O and second is OH bond that corresponds to the both of them. So after that we have performed the fluorescence and the UV spectrum. So in this spectrum we can see that The VO2 VOX quantum dots, they have the fluorescence effect on the 365 nanometer light, and the CO2 have 415 nanometer. Interestingly, in the case of VCO2, they have both on the 365 nanometer, and but the intensity of this peak is very high. So we can use the 365 nanometer light to enhance, to trigger our reaction. And this is the UV spectrum. So in this UV spectrum, we also can confirm that this is the band edge of the VCO2 that is on the 365 nanometer. So it comes that we can use the 365 nanometers light to trigger our reaction. And here we can calculate the band gap. So in the band gap, we can see that the band gap of VCO2 is the lowest band gap. So if the band gap is the low, the response rate and the trigger rate is very high and very fast. So if it can confirm that our prepared VCO2 is the fastest as compared to the alone as VOX and the CO2. After that, we have performed some simulated calculations to characterize our material. Like we have performed the density of state function and integrated crystal orbital accumulating population. So in this case, we can see that the CO2, when the vanadium is incorporated into the CO element, so the band gap has been reduced, the band length, so which can the compact, it has been mounted very strongly, and it has reduced when makes very strong bond. And here the orbital of the also makes in the case of VSO2, the orbital has very close to the Fermi level. That also means the fast response rate, and also the value of the higher isotope value also results the same. After that, we have performed the fluorescence spectra of the VE and the UV by varying the amount and the concentration of the UX and CO2. So when we see that so after that, we have prepared the coatings. So here we have prepared multiple kinds of topping. The first one is the bare coated, and second is the VCO2 coated, but without any material, any color, any dye. But this is the acrylic coating. And in the third one, we have prepared the yellowish color, that is methyl orange dye, to give it some aesthetic properties. And in comparison, we also have prepared the epoxy coatings without any dye and pigment, and we prepared the epoxy coatings with some pigment, that is strontium yellow. So we can see that almost all the coatings have the same width, that is 100 micrometer about, and the surface of the coating is very smooth. After that, we have prepared the contact angle to check the surface smoothness of the coating. So we can see that epoxy coating shows the highest contact angle, and it performs the best results as the smoothness of the coating, because that is anti-water coatings. Here is the mechanism how it can react with the metal ions, corrosion ions, to produce the fluorescence effect. So in this simple mechanism, when our prepared materials react with the aluminum ions, there is the transfer of the electrons from the ground state to the excited state that alter its temperature and produce some fluorescence effect. And when it comes to back the light, when the excited elements come back to the ground state, it emits some light, that light in terms of the fluorescence. So this is the basic simple mechanism of our coatings. So here we have prepared some scratch coatings to initialize the reaction very quickly. So you can see that the pristine coating, they don't have any kind of the fluorescence effect. It is just the effect of the UV light. When we put the all coatings in the light of the UV light, we can see that when VCO2 coated light produced put in the UV light, it shows the scratch part has some corrosion, and that corroded particles shows in terms of the fluorescence, which can be analyzed in very easy method just by the simple naked eye visualization. And same in terms of the dye, that is orange color. So we can see that by adding the dye, the efficiency of the fluorescence has been increased a little bit. So in the comparison, we also have prepared the pristine epoxy coatings. So the same effect in the epoxy coatings, and we can see that the control coatings F and G, they have no any fluorescence effect. But in the case of VCO2 coated epoxy coatings, we can see the bright lines, fluorescence light in the results of interaction with the Corrosion particles. So in next step, we have prepared the coatings that can detect the Corrosion particles underneath the coating. Because when we coat on the some metal structure, we don't always scratch the metal. We need the surface clear. But after some time, this we can also analyze that after the some time, in the initial stages there is no corrosion, so there is no any fluorescence effect. So after some days, some fluorescence particle appears on the surface when we put in the UV light. So we can see the bright particles that are the corrosion particles that increase day by day up to 60 days. And the same effect has been visualized in the colored coating, and also in the epoxy coating, and also in the colored epoxy coatings. After this visualization, we have performed some EIS testing to analyze the corrosion behavior of these particles. So we have grouped into G1, G2, G3 and G4, G5 as is a simple visualization. So we can see that the G1 group, they have the highest impedance and highest impedance modulus. So it means that it has the highest corrosion resistance properties. And in the phase angle diagram, we also can see that there is very smoothness and very little variation in the phase angle. So these coatings are very stable. But in the case of G2, that is VSO2, without any dye. So also results show the same corrosion resistance properties. But in the case of control coating, without absent of the CO2 or absent of the VO or absent of the both chemicals, we can see that the corrosion resistance properties has been decreased after the some days, and that also fails to protect the coatings. So we have also analyzed the parameters like RC, ROX and RCD to further evaluate, confirm our results by using these models. So in the case of epoxy coatings, we also see the same results as in the acrylic coating, but in the case here we can see that the epoxy coatings with the dye also shows us the very good results and high impedance values that shows that it has corrosion resistance against the corrosion. And in the same as the VOCO2 epoxy coating without dye also shows the same results. But in the case of control coating with the absence of the CO2, the corrosion resistance property has decreased just after the 1 day. And in the case of absence of VOX also decrease after the day. And in the epoxy coating, pristine epoxy coating, we can see that there is a great decline in the corrosion resistance properties. So we can say that each component in the coating is very important to protect it, to enhance its corrosion resistance properties. So further, we also again analyze the EIS parameters by using these models, and that also confirms our previous results. On the final stage, we have also performed the corrosion salt spray testing. So in this acrylic coatings, we can see that our main coating, colored coating, it shows very few corrosion effect after the several time. And when we have performed without the corrosion any color, it also shows any negligible corrosion effect even after the 60 days. But in the case of control coatings, we can see that the coatings has destroyed just after the few days, and many blistering has appeared on these coatings that fails against the corrosion effect. And in the case of epoxy coatings, so as the epoxy coating are water resistance coatings, so it can protect better than the acrylic coatings. So you can see that the color coatings has no any corrosion effect, and the scratch particles are also no spreading of the coating appears. In the same case of the epoxy coating without any dye, after the 60 day there is no much any corrosion particles. But in the same, also the control coating also shows no any corrosion spreading of these particles because of the epoxy coatings. So here is the summary that if VOX nanoparticles were synthesized successfully, it has yielding in quick and high fluorescence in efficiency. The VOC coated specimens on the AA2024 T3 specimen were fabricated, and we have utilized these on both acrylic and epoxy coatings. And these processes we also have performed the simulated calculations to enhance the durability of our coating. And the fluorescence coating, they provide the effective alternate to the traditional coatings. So here are some conclusions. So novel, smart, eco-friendly and cost-effective vanadium oxide-based nanomaterials were successfully synthesized as the photogenic coating, and the acrylic coatings are the real monitoring process by detecting the early stage product best by ionization, which is very faster and enhance the duration. In short, the color coatings not only give the beautiful visual appearance, but also can effect protecting from the corrosion in the real-time monitoring, which is very convenient and quick and faster technique. So what are the future product prospects? In the future, we can perform some new materials that can be used in this, and we can use the fluorescence indicators to use on the different metals and different protective coatings. So we can add some additional functionalities into the chromic coatings, and quantitative analysis of the relationship between the corrosion rate can also be investigated, and we can perform more calculations, and we can perform these coatings from laboratory to the commercial scale. So that's all from my side. Thank you very much for your listening. Bye bye.